So, yeah, our next speaker, I think you were here for your first time last year, yeah?
That's right.
And had a very well-received, wonderful talk about the state of antivirus and malware on the Mac. And he's back this year with code signing flaws in macOS, and I am very interested. And like I said, I'm looking around the room, and people right at the front. I know. So, all right, our next speaker is Thomas Reed. Thank you very much.
Thank you.
Big welcome.
Thank you. Well, you guys already know who I am. I work for Malwarebytes. I'm the director of Mac and Mobile there. And that is the last I'm going to mention of Malwarebytes. This is not not about our products at all. It's totally unrelated to Malwarebytes. So just, so you guys know, this is not a vendor talk. So what we're talking about today is code signing flaws in macOS. But before we get started on that, we're going to sort of go back in time a little bit, and we're going to look back at some things that old school malware tends to do. So one thing that some old school malware can do is use a file called rc.common for persistence. So all you have to do is add some malicious code to the end of the rc.common file, and whenever you restart the computer, the contents of that file get executed, your malicious code gets executed. It's a really, really easy way to get persistence. You just cat some command onto the end of the file, and boom, you're done. So it's a one-line shell script, to infect that file. So we've actually seen this in action in some malware relatively recently. It was released this year called MacDownloader. And this malware actually had some unused code in it. You can see that code up there. That the purpose of that code was to actually infect the rc.common file for persistence. Now, this was in unused code. We don't know exactly why it was unused, but the fact is it's there. This was probably in use by something at some point before, perhaps an earlier variant that nobody ever saw. Fortunately, with rc.common, this does not work on any modern systems. I was unable to get this to work on Lion all the way up to current systems, so it doesn't work on anything. But it is something the old school malware used to do, and this was sort of a historic thing from Linux. Cron is another thing that some old school malware uses to get persistence. It's been replaced in modern versions of macOS by LaunchD. So all those launch agents and daemons that you guys are familiar with, that's the new replacement for cron. And cron has been deprecated on macOS for years, but it still works. And we've actually seen this in action in some recent versions of the vsearch or Perit malware on macOS, where it's actually adding a command to the crontab file as the root user to gain persistence. So this is something else old school malware does. Now, since we're talking about old school malware, what about viruses? We've all been told there are no Mac viruses, right? So what exactly is a virus? A virus is actually something that operates by inserting some kind of malicious code into a legitimate application. And it does this partly for persistence, perhaps partly to spread itself. This is very characteristic of a virus, is that one of the main definitions is it has to be inserting itself into some other executable code somehow. There are no, strictly speaking, viruses on the Mac right now. Mac malware is all pretty much Trojans, no viruses right now. There have been some cases in the last couple of years where applications were maliciously modified in order to infect computers. So, for example, the transmission hack from years ago where Transmission was hacked and was distributing the KeyRanger ransomware. There's the Xcode Ghost malware, in which Xcode was maliciously modified, redistributed through file sharing servers in China, and it infected hundreds, if not thousands, of apps in the Chinese iOS stores. There's the recent Handbrake infection and the Ultima software apps that got hacked, all of which to spread the Proton malware. This seems a little virus-like, but there's one critical distinction here. That was done manually, so hackers actually took a copy of the app and modified it, or in one case actually took open source code and modified that and recompiled the app, and then manually uploaded that somewhere for people to download. None of this was automated, so it's really easy to bypass code signatures and that sort of thing this way. So we're going to sort of talk about whether or not this is possible, and before we do that, we want to look at some code signing theory. So how does code signing work? Basically, if you've ever used PGP to sign an email message, this works very much the same way. So you cryptographically sign an application with a private key. At that point, anybody can verify whether or not the application is legitimate or not, whether it's been modified. If its code has been modified, then that signature becomes invalid. It's very easy to test that. And an app that has an invalid code signature should not be allowed to run under any circumstances. There are a couple of Apple tools that will actually give you information about these signatures, and they are both command line tools. The first is the Codesign tool. That's a very powerful and dynamic tool. It can be used to sign applications. It can be used to get information about the signature, to check the validity of the code signature. All manner of code signing tasks can be done with Codesign. The second one is SPCTL. That one actually can also do a code signature check, and it can actually alert you if the certificate used to sign the app has been revoked. Then there are also some third-party apps that you can use to check your signatures. One is What's Your Sign by Patrick Wardle from Objective-C. That's a very nice, very simple app, works through contextual menus. But my personal favorite is RB App Checker Lite, kind of a cumbersome name, but it's in the Mac App Store. It's a very simple, very nice app, and it gives you a lot of information. It gives you more information more easily than any other tool that I know of. So it's one that I really like. So, given code signing and the fact that just about everything on macOS these days is signed, all of Apple's executables are signed. If you're a third-party app developer and you're not code signing your apps, then you're doing something wrong. So pretty much everything is signed these days. So that should mean that viruses are not possible on macOS, right? Because as soon as a virus infects an app, that should be, that invalidates the code signature. Unfortunately, this is not actually true. So let's take a look at some details about how code signing works. And some of this, there are some assumptions that a lot of people have about how this works. And I myself had some assumptions about this up until I started playing with it and testing it. So I think some of this is going to be a little surprising. Most of you guys probably already know that most, as we said, most apps are code signed today. And unsigned apps are not allowed by default. In fact, actually on more recent versions of macOS, they're not only not allowed by default, but they're just not allowed. You can't even set your gatekeeper settings to allow unsigned apps. So when you download a new app from the internet, the first thing that happens when you double click on it is that it verifies the code signature before running. macOS will check that, and if there's something wrong with the code signature on that application, you'll get this message. I'm sure that some of you guys may have seen this before. And it really gives you no option to open it. Your options are to either cancel opening it or move it to the trash. You have no other options. macOS simply does not allow you to open this app, and that's a good thing. You should not be opening an app with an invalid code signature. So that means that these code-signed apps are always safe, right? You're watching, so you know this is probably wrong. It is actually not the case that code-signed apps are always safe. So when you download an app, a little more detail here. What happens when you first download an app is that the app is quarantined. What that means is that the app has this flag added to it. It has this quarantine flag. Some Finder metadata that tells the Finder that particular app needs to be checked out before you can open it. That, you know, the various processes need to evaluate it first. Gatekeeper will check the code signature for quarantined apps. So when you open one of these apps that's quarantined, Gatekeeper checks it, checks the code signature. If it's bad, you're out of luck. After you successfully open an app, so say you've just downloaded an app from the internet, you double-click it, its code signature checks out, everything's good, the app opens up, and the quarantine flag gets removed at that point. After that happens, the code signature is never checked again, ever. You can open that app as many times as you want, and that code signature will not be checked again. So this opens up a bit of a window where hackers can attack you. And the reason that this is particularly bad is malware, it pretty much always wants some kind of persistence. The other thing that it almost always wants is it almost always wants to be hidden. Those are two very important things for malware. If your malware is not persistent, then it's probably a failure, except in a few specific cases, like, for example, ransomware. Ransomware really just needs to run once, do its dirty work, and then it's done. It doesn't care if it's still running or not. But in most cases, malware wants persistence very, very badly. And if it's not hidden, if the user sees it, it's game over. The malware has already failed. So these are two very important things. You can actually achieve both of these goals by infecting an app that has been quarantined or has been unquarantined already. So some app, it's already sitting in your applications folder. You've run it before. It's no longer quarantined. You can actually go in there and modify that app, and nothing bad will happen, at least if you're from the perspective of the hacker. So, and that malicious code that you add to the application will run every single time that infected app is opened. Now, there's actually been one case of malware that sort of used the same technique, except it was manually done. So in the case of that transmission hack where it was installing KeyRanger, what happened was that the dropper, the infected copy of transmission, would install an executable file in a folder on the computer. And then it would execute that file and then delete the file. So the file's gone, there's no trace of it anywhere left on it, but it's still running, it's still resident in RAM, still running in the background. Now, if you restart your computer, then that process is killed and it's gone, no persistence. And KeyRanger actually had a 3-day timer on it. So when you first run it, it wouldn't do anything. It would just start a timer running. And then 3 days later, assuming it was still running, that's when it would start encrypting your files. Now, of course, it couldn't guarantee it would still be running 3 days later. but it could guarantee that you'd still have that infected transmission app on your computer. And if you were running transmission a lot, then you run it again later, that infected, that malicious process gets started up again, and boom, you're hosed. So, but again, this was done manually. We're going to look at how you can do this through an automated fashion through something like a virus. So here's how this works. What you do is you crack open a good app. So we're going to take the example of this app called Good, and you rename the executable, which is good in this case, to something else. In this case, we say 0. Then you put your malicious executable in there, rename that Good. So then when you open the app, that malicious executable is actually the one that gets run. And the good executable, which is of course actually bad, launches the old executable, which has been renamed to 0, in order to make things look normal. So this is kind of what that flow looks like. So the user double clicks on the app that has been infected. The system opens that executable that is actually malicious, that has been placed inside the app. That malicious executable does whatever dirty work it wants to do, and then proceeds to open the original executable, which has been renamed. And this makes everything look normal. So it looks like you double-clicked on the app, and it opened, and everything's good, right? Nothing went wrong. So no suspicions for the user. Unless, of course, you happen to look in Activity Monitor, you might see something like this, where you have 2 processes going. Now, I'm sure that there are ways that you can avoid doing this. This was my first attempt at this. Didn't take me very long to do it. Maybe if I looked a little bit harder, I could find a way so that I could have only one process show up here. But, in this case, for this example, I've got 2 good processes there, which is very strange when the app's only supposed to be running once. And at this point, you're infected. So you're pretty much screwed. So this must be really hard to do, right? I mean, this, creating something like this must not be a very easy process. It's actually really, really easy. Now, I will tell you right now, I am not, by far, not an expert Swift programmer. It took me maybe 2 days working in the evenings after work, doing a lot of Googling, lots of experimentation. And what came out of this was 22 lines of Swift code, not counting comments and empty lines and stuff. So 22 lines of Swift code to build that malicious executable file. Now, obviously, in the real world, if you were actually making malware, that would be a little bit more code because you'd want that malware to be doing something more useful than what my proof of concept did. But 22 lines, that's all it took. And then for the dropper, the infector, I built sort of a 2-part solution to this. One was a shell script that would actually do the dirty work of infecting a particular app. And the other was an Apple script that would wrap that shell script. And the Apple script's job was really just to look through your entire application folder and infect anything in there that it could using the shell script. So, I mean, you could run this and you could infect a whole bunch of things in the application folder, not just one, not just 2. You could have a whole host of infected apps running on any particular endpoint. Now, there are some exceptions to this, fortunately. Apple has done a really great thing, apparently. Apple's apps can't be modified. They appear to be doing some kind of internal code checking. So if you try to infect an Apple app, then it will crash. And if you look in the crash report, it will actually tell you that the code signature was invalid. So this is a good thing. This is what everybody really ought to be doing. And unfortunately, not very many people that I tested a bunch of apps with this, and most of them don't do the same thing that Apple's doing. The bad news in this case, even though the app crashes, which is a big no-no, this alerts the user that something's wrong with their system, and it's particularly bad because you can't run your normal system apps. Nonetheless, the malicious code still runs before that crash happens, because the malicious executable runs first, then the legitimate code, which is what crashes. Some other third-party apps do have similar self-protection, not very many of them, but you see in the example here, I gave the example of Pacifist. If you do this with Pacifist, it will actually identify that it has been modified, and it'll show you, it won't just crash, it will show the user an alert, alerting them to the fact that something is wrong here. So this is actually a lot better than what Apple's doing, but the malicious code still runs every time anyway. So, if you, the average user may see this and just think, oh, I don't know what's wrong, something's wrong with Pacifist, and they've still got malicious code running on their system. Before I skip, let me actually mention one other thing. This actually appears not to work with any App Store apps either. In those cases, those will crash. They don't have a telltale code signature error in the crash log. They just sort of vanish. You launch the app, it pops open and vanishes immediately. But that still leaves a whole lot of room. There are a lot of third-party apps not from the Mac App Store and that don't have any kind of self-protection. So there are some other potential giveaways here. It's kind of cutting off the bottom of my slide there, but you can see in this, you might be able to tell from the top edge of that dock that you've got two icons there. There are two icons for the infected app, one of which was constantly just bouncing up and down. This was in my first iteration of this. Now that's highly suspicious. If the user opens Microsoft Word, for example, and they get two Microsoft Word applications showing up on the dock, one of which is bouncing up and down constantly, that's a big red flag that tells the user something is not right here. So that's obviously not desired behavior. And it actually can be prevented. I found a way to disable that so that you would never see that bouncing dock icon. And that way it's much less suspicious to the user. Another suspicious potential giveaway here, and this one I don't think there's any way around, is if you actually open up Activity Monitor and look at the processes that are running, you can, as you can see, I've filtered here on that good app, and there are actually two processes running there. One of them is named good, the other one is named 0. That's pretty highly suspicious. Again, this is something that you can fix. There are a lot of applications out there these days that have helper tools that are inside the application. So all you'd have to do is, instead of picking the name 0, you pick something like good helper. And if the user sees that in Activity Monitor or in the PS output, they're not going to be at all suspicious. They're just going to think, oh yeah, okay, that's the helper for that app. So, demo time. Now, I've got a little bit of a different demo. I wasn't actually able to get my computer hooked up to the projector here, but I'm going to do a different demo. So here you'll see we've got a good app, which, oh, it opened on the, let me move this over here. There's the good app right there. So totally, not a bad app at all, right? And this legitimately is not a bad app. So how do we infect that? Well, I've got a shell script here that will do the job. So like I said, my full demo would have been actually using an Apple script to infect every non-Apple application in the applications folder. So you could go through and see a whole bunch of different applications all, getting compromised. But we're just going to do it manually this time. So if I run that infector script and I pass it the path, let's see, I need quotes in there. Pass it the path. All right. And now, if we go back here, actually, let me not cancel it. And we open the good app. Oh, look. What's that? Why'd the calculator open up? So, as you can see here, it was really simple to infect the machine. You can't see the dock on here because it's on this screen here, but there's only one icon for the good app, so there's nothing particularly suspicious going on there. If we switch back to terminal, we can do no, I didn't do that right. What did I leave out? Well, you get the idea. There will be two processes running there. And if you want to look at the contents of this infector file, it's really not that complicated. It takes some input. Most of the file actually is just taking input. The one little trick here is you set this LSUI element in the info.plist, and that prevents the malicious executable from popping up in the dock. So, and then the malicious executable itself removes that flag so that the real application actually does show up in the dock again. So it's a little sneaky. All right, let's go back to the presentation. So, obviously this is very bad. This is not desired behavior. The possibility exists for some very, very sneaky malware to get in there and infect machines, infect the applications on your machine, and despite the fact that they're code signed, you'll never know about it. So, what do you do about that? So there are some ways that you can detect that. One is you can use either SPCTL or Codesign to verify the signature. I used SPCTL in this case because it's, it makes really nice terse output. So it was easy to put up here on a slide, but you could use either one. So as you can see in this case, this is a good app. On the top here, you can see you just do SPCTL assess verbose equals 4 and pass the path to the application, and you get back good.app is accepted, so that code signature is good. If you look down here, this is a maliciously modified copy of that same app, and you can see that it says code has no resources, but signature indicates they must be present. That's an indication something is wrong, and that app should not run. You can also, I know that a lot of people here probably are familiar with OS Query and may be using it in your organizations already. So if you do use OS Query, you can use something like this. You can select star from signature where path equals and pass the path to the application in question, and you'll get back this information. So this is for a good app here. It says it's signed. Gives you the identifier, it gives you the team identifier. This is all really good information to have. So, you can see, okay, that is a legitimate signature on that application. And if you know who the developer is, I wrote this application, it's got my developer ID right there. You can confirm that that's mine. And you can confirm from that team identifier that it's actually mine and not just somebody who faked my name. So that's good information to have. OS Query gives you some good info there. In the case of a maliciously modified copy of the app, you'll see right there, signed equals 0. No team identifier, no authority. It's very, very different. That's a suspicious app. That one's been modified. And so OS Query can tell you that. So if you were to go with OS Query, for example, and query all the apps on your endpoint, if you found any like this that were not signed and they should have been signed, you know you've got a problem. You need to check out that endpoint, check out what's going wrong with that app. Because something, probably nothing malicious at this point in time, but at some point in the future, there could be something malicious going on with an app like this. Now, there is a problem, of course. What if the dropper application actually re-signs the modified application? There's not really a whole lot that you can do to automatically detect that without a lot more coding. So for example here, say I have maliciously modified this application and then I've re-signed it. You can see it says signed equals 1 here. So it's legitimately signed. The problem is this is no longer signed by me. This is my app, but it's not signed by me. It's signed by Joe Smith with this other team identifier. The problem is you may not necessarily know what the team identifiers should be for every single app on all of your endpoints. You may not know who the authority should be. So in order to actually automate this, you'd have to have some kind of a database that you'd have to check against and compare, is this the right team identifier for this application? That gets a little bit cumbersome. So although you could do it, it's not a job I would want to do. So there is another solution, and we're actually there's gonna be another talk on this later on in this conference, which I know Tremel talked about, and that is Santa from Google. This is a kernel extension that can do binary blacklisting and whitelisting, and it can do this based on code signature, among other things. That is very, very powerful, very, very useful. So you can use it in lockdown mode, and that will only allow the whitelisted applications to run. So you build up a list of which code signatures, which those team identifiers are legitimate, and you pass those into Santa, give it that whitelist of all the legitimate code signatures. And from that point on, once it's in lockdown mode, those apps will be allowed. Anything signed with a whitelisted signature will be allowed. But any applications that have been maliciously modified, or any applications that have been re-signed with a different signature, will no longer be allowed to run. You can see an example here. This is a copy of that good app, and you can see that it's been maliciously modified here. You can see under publisher here, it says not code signed. So Santa is blocking this, not allowing it because it's been modified. It's still signed with a legitimate whitelisted signature, but because the application itself has been modified and that signature is no longer valid, Santa won't allow it. So that's great. So the big pro to this is really pretty easy to set up as long as you have that list of all the approved team identifiers, approved code signatures. So it's really easy to set up and it's difficult to bypass. If the malware itself can't actually run because it's not an approved application, it's not an approved process, how's it going to bypass anything? So that's very powerful. That's a very powerful thing to have. There are some disadvantages, though. I mean, there's a reason that not everybody is jumping on Santa right now. One of the big ones is that this kind of whitelisting will keep you jumping with user requests. So, you know, Sally in accounting has some new package that she's trying to get a demo of, and it won't run because Santa's blocking it. So she's calling IT to ask you to unblock it for her. You know, that's just one example. I'm sure you'd have, you know, at a big organization, you could have, you know, many requests coming into IT every day for stuff like this. So that can get to be a little bit of a headache. The other thing is, this is really unrealistic for certain developers, for certain users like developers, for example. Developers are constantly running all kinds of weird stuff, unsigned stuff that, you know, downloaded from all over the place, and they are really not going to be happy if you're making them call up IT every time they want to run something like that. So unless you really want to piss your developers off, you probably don't want to do this on a developer box. So within those constraints, Santa can actually be a very good tool. It's just, it's not for everybody. You know, it's very useful, very powerful. And to be honest, you know, I work for an antivirus company. Using Santa could potentially just, you know, eliminate the need for antivirus. Because if it can't run, you know, you're fine. But obviously, you know, not everybody is going to be able or willing to run Santa. So if you can, it's great. And that is it. I think I'm done a little bit early since my demo changed a little bit from what I had originally planned, but that leaves us time for questions and answers. So any questions?
Yes, it does. Yeah, big round of applause first. And I'm sure there are questions, and here's the first.
So, question, I guess this is a question about Malwarebytes, the product. It would seem reasonable to add applications path to the ones that are scanned and just to add the actual check of the signature as the next step if this is...
Yes, absolutely. And that's something that we are looking at, definitely. We're looking at multiple different ways that we can use code signatures to improve our detections. There's an example I was giving to, I think I was talking to Papine earlier. If you guys are familiar with PCVark, they're the company that makes things like Advanced Mac Cleaner, and like they have dozens of other junk apps. Literally, we will detect everything PCVark makes. Anytime they make something new, we detect it. If we could just write one rule to detect their signature, boom, that's it, we're done. They can't run on a Malwarebytes box. So that's one of our goals in the future, is to use that kind of thing to help improve our detections.
Anybody else? Questions? Here we go.
Hi, I write software, and we had a problem where Mac Cleaner would go and modify our bundle by stripping out all the 32-bit code, specifically the driver, and then the driver wouldn't load because the signature wasn't valid.
Yeah.
So I did what you were suggesting, which is put in code right at initialization that checks the signature every time. Is there anything else I should be doing as a preventative measure? I mean, we've been shipping this for a couple years, and all of a sudden all the driver didn't load problems disappeared because we put up a dialog box saying download a new copy, your copy's been modified. So a whole class of tech support instances just disappeared as soon as we did that.
Absolutely.
Is there something else we can do?
I think actually checking the code signatures is it's really important. It's probably the best thing you can do. I did mention the possibility of malware re-signing with a legitimate certificate.
Mm-hmm.
I think that's a little bit of a stretch. I don't think that's likely to happen, mainly because that will require the malware to actually include a private key within the malware, which could, that could be, it basically puts the malicious, the malware author's private key in the hands of anybody out there
Right.
who gets a hold of it.
The other thought I had was
So-
checking for 2 executables in the macOS folder.
Yeah, yeah. So like, I think it's less likely that you'd see things getting re-signed so that they would show up as having a legit signature. It's far more likely that you would see things getting modified and invalidating the signature. So if you're checking those signatures all the time, then that's a really good solution.
Okay.
Anybody else? There are lots of questions. Yeah, actually, I'm going to follow the traveling salesman shortest path first. So.
You mentioned that the App Store apps didn't work. Did they not start up at all, or did it? Are they doing some sort of signature validation on every launch?
Yeah, I'm not sure what's going on with the App Store apps. They simply, like, what would happen is the malicious code would launch, it would go to launch the good code, and it would just pop up and disappear again. So it was some kind of crash, but it wasn't leaving the same crash logs that, for example, a maliciously modified copy of iTunes would.
But the
So
malicious code did run.
the malicious code did run, yeah,
Okay.
yeah. In every single one of these cases, the malicious code actually did run first before any kind of alerting or crashing was happening. So
That's a really important, interesting distinction.
yeah.
Wow.
Possibly, yeah, possibly. I didn't really dig into that in detail because I only kind of discovered about it last minute when I was trying to set up my VM with the demo, and a couple of the apps that I was testing with were Mac App Store apps. And I was like, well, why aren't these working? So, yeah, I didn't really dig into the cause and effect there.
All right, I saw someone over here with a question. There we go.
The Flocker utility would let you set up a rule so you couldn't modify the application folder by any
Which
process?
utility?
Flocker?
Flocker.
Flocker,
Yes, I believe so. Now that Flocker actually, little Flocker
Little Flocker, yeah.
no longer exists at this
It's-
point. If you had an old copy of it, then yeah, it's
I think it's being picked up by another company, I'm not sure.
right.
They
Yeah,
haven't
so
released it yet.
it's gotten picked up. I think it's F-Secure has it now. I forget what they've called it. They've integrated it with some of their own software now, and they have a different name for it. Next Fence. X Fence. That's
Okay,
right.
yeah.
So, I mean, yeah, that can do something similar, but it's not quite the same as what Santa does. It's a little more, Little Flocker is more like if you're thinking of Little Snitch, but instead of for outgoing network connections, it's for the file system accesses. So it's, instead of just checking code signatures, it's looking at things like, you know, should you be able to open that file? Should you be able to write to that file? Should you be able to, you know, delete that file, that sort of thing.
Also, isn't SIP supposed to prevent access to critical areas of the file structure?
Yes, it does, but not to the applications folder and not to a number of other places where people would install executables.
Okay.
So,
Thanks. Anybody else?
Actually, no, I rescind my.
Okay. Yeah, there we go.
So I'm wondering why it is that Apple wouldn't have stomped on this already. Is there a good reason why they wouldn't be monitoring the application folder in a more pervasive way?
yeah, I actually, several months ago, I actually talked to Apple about this when I found out how this works, and basically I was told that it's working as designed. However, the guys that I was talking to did seem a little surprised that it didn't cause a crash. They thought that it should have caused a crash, and it did for an Apple app, but not for our third-party apps. So, but yeah, what I was told was that checking the code signatures every single time an application launches could potentially cause a performance hit on your system. So it's working as designed. I don't know whether they'll, I did submit all of this to Apple, so I don't know whether they will change their minds about that after having actually seen my demo, because I passed along my code, my example infector, and all of this stuff. So that might change their mind. We might see some change to this in the future. Yeah, you
go. Oh, wait for the thing. The thing. You need the thing. Yes.
Okay. So if malicious code is running in an app and the user is a non-administrator, what's the extent of the damage that can occur? Is it just limited to the user sandbox then?
Yeah, so if the actual executable file it doesn't have root access of any kind, then yes, it can not damage anything outside the user's folder.
What about if that person is an administrator on the machine? Will it trigger an authentication request?
Even if it's an admin user, unless your malicious code actually asks for those elevated privileges, it can only access user folder stuff. Still, that's where your most important stuff is. That's an important distinction, is that a lot of people think, oh, well, if you can't get root, it's not that big a deal. But it really is. I mean, if you can't get root, it does not matter at all. It's, the data in the user folder is really what most malware is interested in, either stealing it or encrypting it. So root permissions really are not that important these days, especially if you can get persistence by hacking a whole bunch of apps in the applications folder without root.
All right, thank you, Thomas. I think
Sure.
you're going to be here till Friday, right?
Yeah, if anybody else
Right on.
has any questions, I'm here. I fly out Saturday morning, so I'm here all the way through Friday evening. Just corner me somewhere and ask me any questions you want.
Fantastic. Another big round of applause. Thank you.
Thank you.